Welcome to Brain Vision.
For this question, we have two wires carrying a current, and these wires are separated by a distance d of 20 centimeters or 0.2 meters apart. The top wire, which I call wire 1, has a current I sub 1 of 20 amperes, and the bottom wire, which I call I sub 2, has a current of 12 amperes. And what we're asked to do is we're asked to find the magnitude of the magnetic field at a point that's halfway between them, considering this information. So first we'll find the magnetic field produced by the top wire at that point. So we'll call this magnetic field B sub 1. And our equation for magnetic field is mu naught, which is the magnetic permeability of free space. It's 4 pi times 10 to the minus 7 newtons per ampere. You can look that up if you want to know more about that constant. So it's mu naught times the current, which is I1, times 2 pi times the distance that we're considering. But the distance is halfway in between the two. The distance between the two is d, so halfway would be d over 2. So we plug d over 2 in. Plugging those values into this expression, we find that the magnetic field is 4.0 times 10 to the minus 5 Tesla. Now we're going to do the exact same thing for the bottom wire. We'll call it that magnetic field B2. And it's the same equation, except for this time, our current here is I2, the current in the bottom wire. So it's mu naught I2 over 2 pi times the distance we're considering, which again is halfway in between the two of them. So this is d over 2. So plugging all those values in, we find that the magnitude of the bottom wire's magnetic field at that point is 2.4 times 10 to the minus 5 Tesla. So then to find the total magnetic field at this point, we'll start a new page since we ran out of room. We'll call this B. We simply add up the sum of the squares of B1 and B2 and then take the square root. So this is the square root of B1 squared plus B2 squared. Plugging those values in, we find that the total magnetic field is 4.66 times 10 to the minus 5 Tesla. And we can box that in as our solution to the question.